Okay. Hello, lovely people. We'll get started. This is just to go through this week's stuff. I'll just check the audio so I know that somebody can hear stuff. Awesome. Okay. Hello and welcome. Okay. This week we're building on last week. So last week we looked at first principles, and we discovered what the derivative was from the very first principles. Now we're going to look at that derivative to find the equation for a tangent to a curve. Okay? So, just to go back a step, from first principles, if you have a curve that's x squared, okay, you can find the derivative at any point along the line using the derivative formula. Okay, we can do that from first principles by looking at what is the rise between this point and its own limit. Okay, between the x value at this point and its own limit, and decide that this is the instantaneous rate of change. Okay, so the formula goes the limit as h approaches 0 of the function, which in this case is x squared. So the function on top plus h. Okay, so because he's squared, we've got to square that to find the change in x between x plus h and x squared over x plus h minus x, which just cancels to h. Okay, so we're looking at the up and down difference as we've gone across our little horizontal distance between x and x plus h. Okay, so factoring this out, we go to x squared plus 2x plus h squared, that's all of him squared, minus x squared on h. Our x's cancel. I forgot to put a h there because I'm a bad person. And we're left with h outside of 2x plus h. H on top of h cancels out to 0. We're left with 2x plus h, so 2x as h goes to 0. Okay? Now this is a long process to do every single time when you're finding a derivative. So what we can skip ahead to is called the power rule. I'm just going to write down the power rule and show how it works with that one, and then just do a little bit of a brief explanation on how you can get to that one to every other instance of squareds and cubes and to the power of 7 and whatever else. And then we might look at some sort of something even beyond that if we get time. Okay? So, power rule works for powers. So it should be x to the a, where a is like a number. Okay? The derivative, so dy dx of x to the a equals a x to the a minus 1. Okay, so whatever he is, you times him by the coefficient in front of x, and then you take 1 off the power. take the index times by the coefficient, take 1 from the power. So here we had an index of 2 for our x squared. We took 1 off 2, we got to 1. And we have 2 lots of x to the 1. Okay? Now, this comes from the relationship with Pascal's triangle. And essentially, every single power expansion can be done in Pascal's triangle, and we're using a pattern from Pascal's triangle to identify the power that we need. So if you have Pascal's triangle, it goes to the power of 0, is just x, so you're left with, is just 1, so you're left with 1. Okay? 1 is x, 2, and the expansion of x plus h to the power of 2, which is what we did here, gives you x squared plus 2x plus h squared. Okay? Now the same thing to the power of 3 is 3x cubed plus, is x cubed plus 3x squared plus x squared h plus 3xh squared plus h to the 3. Now I'll do one more of these because I'm killing myself with room. But if you expand x plus h to the 4, you get x to the 4 plus 4x cubed plus 6x up 4x cubed h plus 6x squared h squared plus 4x h to the 3 plus x to the 4. Plus h to the 4. Now you'll notice that in this expansion, the term after the first term always starts with the number of the power. So it went from 2 to 3 to 4, and that comes with Pascal's triangle and that adding up to find the term below. So 2 to 3 to 4. And this one was always h. Now all of these at the front cancel because you're always going to have this first step. You're always going to have this first step of the function or the power, take it at the point before. Then you're always going to have the second test step of this second one is 1 less on the power of Pascal's triangle and has like 1 more h. And then the rest have got like h to the 2, h to the 3, h to the 4, h to the 5, h to the 27. Okay? But you've always got that squared bit. Okay? You've always got the one that's the leading thing in Pascal's triangle being cancelled. You've got that second one, which follows the power rule up here. And then you've got every other one, which gets doofed because it's got too many h's that disappear as the limit of h approaches 0. And that's why there's a power rule. Okay? So that's the power rule. And that's a little bit on where it comes from. Now let's work on using it. Okay? So power rule again. is dy dx of, I'll put an a out the front this time just to show you that a can be the coefficient, x to the n. So when we're defining the derivative of something x to a power, we take the n and we times it by a and then take 1 off the n. So we have na x, we take him, we times him by him. We still have our x, because that's the thing that we've got in our equation, and it's to the n minus 1. Okay, now that's the power rule. Okay, so I'll do a few just to get you into the habit, though you guys should pick up the habit of this pretty quickly. Okay, so the habit goes like this. If I have 3x to the 2, and this is our dy dx, so this is our, actually, we'll call this our function. So f of x and dy dx is our derivative of that function. So we end up with our function being 3x squared, take 2 times by 2 minus 1. So we end up with 6, 3 2's to the x to the power of 1. Okay? If you have 3x, you're going to end up with 3. Because there's an imaginary 1 here. 1 times 1, so 1 times 3 is 3. And then x to the 0, because 1 take 1 is 0. And you're left with just 3. Okay? There's some ones that people might find confusing. If you have 1 over x, he can be a bit confusing. Yep. So this is x to the minus 1. So our derivative is minus 1x all to the power of minus 2. Minus 1, take 1 is minus 2. Hopefully that all makes a degree of sense. Okay? That's the power rule. Using this power rule to find a derivative, a tangent to a curve. Okay, I'm going to do this with x cubed. So we've got x cubed. Okay, we're going to find a tangent at the point x equals 2. Okay, so that's our question. We've got to find a tangent to the point x cubed at x equals 2. Okay, I'm going to need a few rules for this. I'm going to first of all need the power rule, and then I'm going to second of all need to know my equation of a line, which is y equals mx plus b. Okay, and with those two things, should be able to work this out, no worries. Okay, so first job, find the derivative of x cubed, which you can see from the power rule, dy dx equals 3x squared. Okay, that is our derivative. But we don't have dy dx in this formula. So we've got to go from dy dx to an n. Okay? Now, n at the point 2 is going to be chucking 2 into this equation, and we'll get m. So m equals 3 times 2 squared, 3 fours, m equals 12. Okay? Now we have our 12, we can put 12 into this equation. Okay, but I first of all need a y value, so I can chuck y in and work out what the intercept is. Our final little bit, our b. So that's what I'm going to do. If x equals 2, 2 cubed is 8. So y equals 2 cubed, which equals 8. Okay, and I just got that because this is our function. Cube it, you get your y. Okay, so when x is 2, y is 2 cubed, which is 8. So now I have 8 going into this formula here. 8, my y, equals 12, my n, times 2, my x at the 0.82, plus b. So 8 equals 24 minus b. So with 8 equals 24 minus b, b equals 16, negative 16. Okay, so y equals mx plus b. B has to be a negative number, and 8 equals 24 minus 16. So your b is minus 16. Okay, that's not my answer though. I can put it into my calculator, and I get y from this formula equals m, which is 12, x plus, minus 16. Okay, now you may be required to draw this to show that additional understanding. Okay, so this is your cubed. This would be the 0.28. The red line would be tangent. And he goes and he follows the thing. So this point is minus 16. Okay, it goes from the 2.28 to minus 16. Okay, and that is pretty much all for today. As I said, it's a bit of a quiet week, this one. Key things you need to understand is have a thorough understanding of that first principle stuff. Okay, it's all key, the first principles. It leads you to the power rule. In fact, in hindsight, it's probably clearer if I just label this f of x, and this is dy dx. Okay, when you see dy dx of something, you've got to find the derivative. Okay, that's a bit of notation. Power rule comes from Pascal's triangle. The more you understand Pascal's triangle, the more you'll get power rule. Okay, it's essentially whatever's up here, times in by the front, and then take one off, and you can't go too far wrong. Okay. This is a few examples of the power rule. One that I forgot to do is, say you've got x outside of root x. Okay, this is probably about as confusing as the power rule gets. X times root x because this is x to the power of 1 times x to the power of half. Add the powers, x to the power of 3 over 2. Times in by the front. So you're left with 3 on 2. X to the power of a half. Okay, and that's it. Hopefully there's no questions. I'll go through the same thing in class. Okay, so if you've got any questions that come up over there, but that should be enough to get you into the swing of answering some stuff in that booklet. If any questions do come out of that, please do ask. Bye guys.